Okay, so welcome to Xline community meeting, and the topic of today's meeting will focus on consistency and performance in Xline. So why is this topic important? The topic is important because we are currently undergoing a major rewrite of the Xline project, which will be rolled out in version 0.7. And we want you to know about what is going on in this rewrite. And most of specifically, this rewrite involves fixing some consistency issues that currently exist in Xline. As you can see, there are some issues about the failed Jepson tests, and another major topic will focus on how it improves the system performance in Xline. So how is the performance of Xline right now? And you may notice Xline currently have some scaling issues under heavy load, and we have resolved them in this refactor. So first, I want to demonstrate a plot of the put benchmark in Xline before and after the refactor. And you can see there's a huge performance improvements, and the put throughput has been increased by 20 times in some cases. And we also have a comparison to etcd, and we can see that the throughput of Xline is comparable to that of etcd, and even surpass it in some cases. So next, I will discuss the details of some major rewrites in Xline codebase and explain how do we achieve these improvements. So the first major factor is how the curb log is persistent. So the curb log is identical to raft log. It is used to ensure data consistency across reboots or power failures. And in this section, I will explain some issues in current log persistent implementation and the new refactored implementation. I'll first show you how the current approach of log persistent mechanism. So in current implementation, we have a dedicated log persistent task for persisting the logs. It communicates with the curb node through a channel. Once the curb node receives a new command from the client, it will send the log to the persistent task, and it won't wait for the log to persist, but directly execute the command and send the result back to the client. So you can see that the persistence of the logs happens asynchronously, and this will cause some issues. The first issue is that because the key value persistent can happens before the log is actually persistent. If a node crashes, the state of the key value storage could be newer than the log storage. Then during the recovery, it may cause inconsistency between the log storage and the KV state machine. And there's another issue with async log persistent. It is the cluster may lost some log entries if the majority of the cluster restart. For instance, if you deploy some Xline nodes in a single data center and there's a power outage occurs, then you could potentially lose your data. Also, there's some performance issues in the current implementation. First, Xline uses RocksDB as its log storage, but that's not a very good idea because RooksDB does not provide fine-grained fsync control, which means you cannot call fsync on every write to the database, and you may lose some data during a sudden power loss. And the second issue is that there's no batching in the current persistent approach because Xline will persist each log entry separately, and it will cause doing a lot of system calls on the heavy load, which has a huge impact on performance. So to resolve the consistency issue in the log storage, we switched to synchronous log persistent, and we implemented a write-ahead log as the log storage. There are several benefits of using a write-ahead log instead of storing all the entries in a database. So the first advantage is that the log storage only requires the implementation of a simple operation, that is appending the log to the back of the storage. In the write-ahead log implementation, a log entry is serialized and directly append to a file. And the second benefit is that we can have the flexibility to implement our WAL with fine-grained fsync control. We can perform fsync on every write to the log file. And the final advantage is that we can attain a higher level of data consistency by using checksums for each piece of data written to the write-ahead log storage. Next, I want to discuss about the safety of the WL storage. We would like this implementation to effectively manage various type of errors. Meanwhile, we also need to make some safety assumptions about the system. First, we assume that the latent errors can occur. A latent error refers to silent corruptions in the storage devices or file systems. Additionally, we do not assume that a sector write is atomic or that a power-safe all writes are guaranteed. And a power-safe all writes means a write could not damage data outside the intended range. And to ensure data consistency in these circumstances, we include a checksum for each piece of data written to the write-ahead log. Additionally, we rely on the assumption that fsync is always reliable, because given that it is already a best effort, and there's nothing we can do if the system behaves incorrectly. So while data consistency is our top priority, achieving high performance in the WL storage is also crucial. I understand you may concern about the potential performance impact of transiting from asynchronous to synchronous versions, but it's generally not an issue. It is mandatory to call fsync on every write to the write-ahead log, and the latency for fsync on SSDs is usually lower than 1 milliseconds, but a few hundreds of microseconds per fsync is not enough to achieve high throughput. We still need to batch the entries before sending them to the write-ahead log, so that the average time for processing each entry will be minimal, especially during periods of heavy system load. Okay, the next part is the conflict check refactor. The refactoring this time involves the conflict checking mechanism, and it's mainly focusing on the refactoring of the conflict pools of the curve node. I will begin by providing you with some context on the conflict pools in Xline. So the curve protocol requires the node to record commands in some data structures, and these data structures is used to determine the commutativity among the commands. And commutativity means that the sequence in which the commands are executed does not affect the final outcome. So we can see that if we put a put of x1 does not commute with put x3, but it does commute with put y2. In Xline, there's two types of conflict pools. One is the speculative pools, aka witness in the curve protocol. And a speculative pool is used to store all the commands that commute. And the other is the uncommitted pool. And a uncommitted pool is used to store the commands that haven't got synchronized to the majority of the cluster. So the primary concern is the performance issues in the old conflict pool design, because it is uh, on the critical path of the entire proposed process. In both the speculative and the uncommitted pool, you will need to iterate through the entire pool to check for conflicts. You can check the API of the speculative pool. Although the insert and remove will only takes all of one, as it uses a hash map to store all the commands. The time complexity is O of n for single conflict check operations, which is very time consuming, especially when there are a lot of commands inserted into the pool. And in the new conflict pool design, we use a interval tree to maintain a set of commands. And for key value operations specifically, it will record the key ranges of the commands. Uh, the interval tree is a self-balancing binary tree which supports dynamic insert, remove, and query overlapping intervals. So you can identify three types of key value operations. The first one is put, and second one is range, and the third one is delete range. And all these operations contains a range. So you can use an interval tree to manage a set of ranges in a and so because you can map the ranges to the interval of the tree. So using an interval tree to manage this set of intervals is a practical approach, because the worst case time complexity for each of these operation in the conflict pool is O of log n, which is sufficiently fast for our use case. Okay, let's proceed to the next section. This section includes the command worker and the conflict check npmc in Xline. As usual, I will first explain the current design of command execution. When the curve node receives a command proposed from the client, it first sends the command to the conflict check channel. And this channel is responsible for maintaining dynamic conflict relationships. For instance, if you send two commands to the channel and they do not commute, they will go out of the channel in the sending order. However, if the two commands does commute with each other, they can go out in any order. So once the command leaves the channel, they are sent to the command workers. These workers are responsible for executing the commands and persisting the results to the state machine. Also, next, I will talk about the consistency issue we found in Jackson test. One of the key objectives of Xline is to maintain compatibility with etcd. And in etcd, it employs revisions to signify the key value storage as a state machine. Our current design of the command execution, as I previously explained, allows commands to exit the conflict channel in an arbitrary order. So this departure from strict serializability guarantees will result in a failure in the Jepson tests. So in addition to the consistency issues, there are also performance problems in current design. The first issue is the complexity of the conflict channel is too high. The inner representation of the channel is a directed acyclic graph of commands, conflict relationships. The conflict check procedure in the channel is essentially performing a topological sort, and this procedure results in a time complexity of O of n square for the graph construction, which is highly inefficient. And another concern is the unnecessary command workers. Uh, because Xline is built on the Tokyo runtime, and the runtime by default spawns a number of workers threads equal to the number of CPU cores available to the system. And in the current design of Xline, uh, it will spawn workers to handle commands received from the conflict channel, and this is redundant because there's no need to implement a worker pattern on top of another worker pattern, as it only introduces extra overhead. And so in the new approach, we simplified the command execution design. First, we removed the conflict check channel and shifting that responsibility to the conflict pools. The command workers are also removed, and the command execution will now take place in the curve node. It will directly execute the command in the same Tokyo task when there's no conflict. And the command workers is also be simplified to a single after-sync task. The after-sync task is responsible for receiving the command from the curve node and persist it to the KV store after the log has been committed. In the after-sync task, all commands are serialized to address the consistency issue I mentioned earlier. Meanwhile, commands are batched while persisting to the key storage to reduce the write overhead, and it is significantly better compared to uh, concurrent writes to the backend database. So next part is the client propose refactor. The client propose stage involves the client sending the commands to the cluster. I will explain some details about how the client propose work in the curb protocol. So in curb, the client will first send a proposed message to the cluster, and there will be two possible results. The first result is that there's no conflict. Then the command will be considered committed, and there may some another situation is that a conflict is detected. Then the client must ask the leader to sync the commands to followers. So in the implementation of Xline, the client will simultaneously send two unary gRPC requests to the leader. One is for proposing a request, and it contains the actual command, and the other is for waiting for synchronization. It will returns to let the client know that the command is committed, uh, and it only used if a conflict is detected. And the leader provides an execution result and an after sync result in response for the two requests respectively. Uh, so why does the gRPC performance matters? You can see that a typical throughput of put request for etcd is like tens of thousand query per second, and the get throughput could be hundreds of thousand queries per second. So the gRPC server will consume a lot of CPU time, even for a multi-core platform. And Xline needs to send two unary requests to the leader currently. However, for a Raft implementation like etcd, the client only needs to send a single request to the leader, and it will await the synchronized response. So the current implementation in Xline leads to approximately half the throughput for the gRPC server in comparison to the Raft implementation. So this reduction in throughput occurs because the server has to process two requests instead of one. In the new approach, we have switched from unary requests to gRPC streaming because it is evident that the server needs to return a fixed number of results, the execute result and the after sync results. And in this scenario is well suited for using a stream. The client will opens a new gRPC stream for each propose, and it only needs to send one message to the server. As a result, this design could simplify the implementation of both server and client. In the old unary implementation, the request response pattern requires the leader to store the result for each operation before sending them back to the client. However, if you use the streaming approach, the server can immediately send the result to the stream, so it don't need to store them. And the client implementation can also be simplified. And in the old implementation, the client need to implement two set of handling logic for the two results returned by the unary request. But by using a single logical stream, the client can easily decide whether to receive one or two messages from the stream. So in the final part of the topic, I would like to discuss the lesson we learned from this refactoring process. The first one is the blocking operations are not always harmful in async runtime. So the first is the write-ahead log implementation. Our implementation uses fully synchronous code because it will only blocks a few hundreds of microseconds, and it shouldn't be considered to be a real blocking operation. And actually, we initially implement the write-ahead log using async code, but we discovered that it was causing a very high latency in fsync calls. This was due to the Tokyo actually moving the fsync operation to another blocking thread, which is very expensive. And finally, using blocking operations of the write-ahead log directly in the runtime makes sense because without persisting to the log, the system will be unable to make any progress. And another lesson is that you should always batch the locking and I/O operations. As I already mentioned earlier, because this can help you avoid the lock convoy issues, as as the batch only happens in a single thread, and you don't have to call in multiple threads, which can relieve the lock convoy problems. And in the meantime, it can also reduce the overheads of using too much system calls. And finally, batching I/O operations are also more friendly to the storage hardware. And the third thing we learned is that just don't use interior mutability in Rust unless there's no other way to do it, because interior mutability will make the API hard to understand, because you cannot tell whether an operation will actually mutate the state of the structure from the API. And additionally, it will make it harder to reason about the internal locking behavior. And finally, it will be more complex to batch the operations, as you won't be able to control the logs as the API hides them. And the next part is to avoid allocations. We have a huge performance gain after switching to the JEmalloc allocator. And we notice there's a lot of small allocations, such as arc new and vet clone, and they generally scattered throughout the code base. And some of these allocations are located on critical paths and even while holding a lock. Therefore, it is essential to minimize or relocate these allocations to enhance the overall performance. And the final lesson is that you really should think twice before using a lock-free data structure. A lock-free version may not always be a drop-in replacement of of the original data structure, and we have experienced two lock-free data structure that would actually slow down the performance. The first one is dash map. Dash map is a concurrent hash map implementation, and it will use the arc internally. So the dereferencing time will be significantly slower, and we observe much slower iterations through the map compared to a hash map with a lock. And the second data structure is uh, a skip map. And we found that it is twice as slow as a B-tree map when it comes to a single insertion and removal operation. This performance difference is primarily due to the fact that skip map is less cache friendly in comparison to a B-tree map. Uh, Therefore, if you don't need a concurrent modification to a data structure, uh, using a lock will usually be more performant. And one final note is that those refactors may not have been submitted as pull requests. If you are interested in the new code or wish to make a contribution, please feel free to reach out to us. Um, and thanks for your time listening and any questions.